In the past few lectures, we have been discussing boundary layer theory for the flow past a flat surface at which the velocity decreases to 0 at the surface. If you recall, we had examined first the flow past a flat plate with a heated section, okay, in which the velocity is increasing linearly from the surface. Okay. And then we had discussed the flow past a spherical particle, okay, in which there is a free stream velocity towards the surface, and in this case as well the velocity decreases to 0 at the surface. Okay. In both cases the velocity decreases to 0 at the surface, and in both cases there were some common features that we had found. Okay. In both cases, if you recall, the Nusselt number correlation was the Nusselt number is equal to 0.81, okay, Pe power 1/3, PEL, okay, where L is the total length of the surface. Okay. The Nusselt number was equal to 0.992 Pe power 1/3. Okay. In this case, the Peclet number was equal to the free stream velocity times d by alpha. Okay. In this case, the Peclet number was based upon the strain rate, if you recall, okay, Vs prime L square by alpha. Okay. Okay. So, in both cases the Peclet number, it was proportional to Peclet number to the 1/3 power. Okay. In both cases we had defined the similarity variable as eta is equal to the cross stream coordinate, okay, z by delta x of x, okay, or eta is equal to r star minus 1 by delta star of theta. Okay. And in both cases we had got an equation of the form, okay, minus eta square dt by d eta is equal to d square t by d eta square, okay, times some equation that resulted in an equation for the boundary layer thickness as a function of the streamwise coordinate. Okay. So, this was once again a common feature. In this lecture, we will try to examine why these come about, okay, why these common forms come about. Okay. So, let us just consider a general surface, okay, a general surface which has some curvature, okay, and let us assume that there is some flow, okay, which has a no slip condition at the surface. Okay. So, the velocity decreases to 0 at the surface. The surface is at temperature T0, the fluid is at temperature T infinity far from the surface, and the flow is sufficiently fast that the temperature disturbance is restricted to a thin region close to the surface, okay, in both cases. Okay. If the thickness of the boundary layer is much smaller than the radius of curvature of the surface, then you can consider the surface to be locally flat, because we are interested only in a very thin region close to the surface. Okay. So, in that case we can consider the surface to be locally flat, okay, and use a coordinate system which is whose two coordinates are parallel and perpendicular to the surface. I will use z here because that is what I have been using, are parallel and perpendicular to the surface locally, okay, and analyze the problem in this coordinate system. Okay. As usual, you would scale eta is equal to z by delta x, okay, that is a similarity variable, t star is equal to t minus t infinity by t naught minus t infinity. Okay. The velocity at the surface has to be 0. Therefore, the velocity close to the surface has to decrease, it has to increase linearly from the surface. Okay. So, therefore, the velocity in the x direction, the streamwise velocity has to be of the form Vs prime times z, okay, where z is the distance from the surface, and Vs prime, which is in general a function of x, is the strain rate at the surface. For the flow past a flat plate, the strain rate was constant, whereas for the flow past a sphere the strain rate at the surface was changing with the angle theta. Okay. So, in general this Vs prime, the strain rate at the surface is going to be a function of the streamwise coordinate x. Okay. So, this strain rate is Vs prime of x times z. Okay. What about the velocity perpendicular to the surface? We know that the velocity for an incompressible fluid has to satisfy the incompressibility condition, that is the divergence of the velocity is 0. In this particular two dimensional coordinate system, this implies that partial Vx by partial x plus partial Vz by partial z is equal to 0. Okay. In the two dimensional coordinate system that we are considering here. Okay. So, substituting this expression for Vs prime, okay, you can express partial Vz by partial z is equal to minus z into dVs prime by dx. Okay. I told you that the strain rate at the surface is in general a function of the streamwise coordinate. Okay. The strain rate at the surface is in general a function of the streamwise coordinate. So, this is dVs prime by dx. Okay. And if I integrate this once, I will get, okay, Vz is equal to minus z square by 2 dVs prime by dx, okay, plus a constant of integration. That constant of integration has to be 0, so that the velocity is 0 at the surface, the no penetration condition. Okay. So, to ensure that the no penetration condition is satisfied, the normal velocity is 0 at the surface, the constant in that expression has to be 0. Okay. So, we can substitute these two approximations for the two components of the velocity into the energy balance equation. Okay. We will substitute these two contributions into the energy balance equation along with the expressions for the temperature. Okay. Recall that we had substituted eta is equal to z by delta x, okay, partial t star by partial z, okay, is equal to partial eta by partial z dt star by d eta, okay, chain rule for differentiation as usual, okay, which is equal to 1 by delta x dt star by d eta. Okay. That is the first derivative. The second derivative d square t by d z square is equal to 1 by delta x square d square t okay. And then we also have, if you recall, the expression for the temperature gradient in the x direction, okay, so that I can write it as partial t by partial x is equal to minus z by delta x square d delta x dx, right, times dt by d eta. Z by delta is eta, so I can write this in terms of eta as minus eta by delta x d delta x by dx. Substitute that into the conservation equation. Okay. Vx partial t by partial x plus Vz partial t by partial z is equal to alpha times partial square t by partial z square. A balance between convection and cross stream diffusion in the boundary layer. Okay. And I substitute my expressions for Vx and the derivatives. Okay. So, these are the expressions for this is the expression for Vz and this is the expression for Vx. Okay. So, the first term here Vs prime z, okay, into minus eta by delta x d delta x by dx dt star by d eta. Okay. That is Vx times partial t by partial x. Okay. And instead of z, I will substitute eta times delta of x. Okay. Okay. Instead of z, I will substitute eta times delta of x. Okay. Plus the second term, okay, plus Vz. Okay. Recall that Vz is minus z square by 2 dVx dVs prime by dx. Whereas Vs prime is the strain rate at the wall, okay, times partial t by partial z, okay, times 1 over delta x, okay, dt by d eta, okay, is equal to, on the right side I have alpha by delta x square d square t by d eta square. And once again for z I can substitute delta eta. Okay. Divide throughout by the prefactor on the right, so that the coefficient of the term on the right becomes equal to 1. Okay. And if I do that, you will see that I will get some common factors here. Okay. Note that both terms on the left are both proportional to eta square dt by d eta. Okay. Both terms on the left are proportional to eta square times dt by d eta. Okay. So, I will get a common factor of minus eta square dt by d eta. Okay. On the right I have d square t by d eta square, and on the left I have a prefactor. Okay. On the left I have a prefactor, okay, which I can express as, okay, Vs prime delta x square by alpha d delta x by dx, okay, plus delta x cubed by 2 alpha d Vs prime by dx. Okay. So, this term has to be order 1 in the limit as Peclet number becomes large for a similarity solution. Okay. So, this is the equation for the boundary layer thickness, okay, which is required in order to obtain a similarity solution. Okay. And you can see that these two terms are the same as what we had got earlier. Okay. These two terms are the same as what we had got earlier, both for the flow past a flat plate and for the flow past a spherical particle. Okay. And we had solved that to get T star is equal to 1 minus 3 power 2/3 by gamma of 1/3 integral 0 to eta d eta prime e power minus eta prime cubed by 3. Okay. Okay. And the surface q z at z is equal to 0 was equal to k into T naught minus T infinity by delta x 3 power 2 by 3 by gamma of 1/3. So, this is the reason why we had got the same expression, whether it was for flow past a flat plate or for flow around a spherical particle, because in both cases you can reduce the equation to this particular form. Okay. This is a general result. The equation for the boundary layer thickness has to be obtained by solving this one. Okay. The equation of the boundary layer thickness has to be obtained by solving this. Okay. This is set equal to 1 without loss of generality, and I can re-express this as Vs prime delta x by 3 alpha d delta x cubed by dx plus delta x cubed by 2 alpha d Vs prime by dx is equal to 1. Okay. I have just re-expressed delta square d delta by dx as 1/3 d delta x cubed by dx. Okay, that is all. Okay. And I divide throughout by this prefactor here, divide throughout by this prefactor here to get a first order differential equation inhomogeneous for delta x cubed. Okay, plus 3 delta x cubed by 2 Vs prime is equal to 3 alpha by Vs prime. That is the first order inhomogeneous equation for the boundary layer thickness. Okay. Integrating factor, okay, is equal to e power integral of dx times 3 by 2 Vs prime, okay, dVs prime by dx. Okay. That is the integrating factor, that is this prefactor here. Okay, that is this prefactor here, that is the integrating factor. Okay. You can carry out this integral quite easily. Okay. Integral dx of 3 by 2 Vs prime dVs prime by dx. Okay. This is basically equal to integral dx of I can take the 3 by 2 here, okay, of d of the natural logarithm of Vs prime. Okay. 1 by Vs prime dVs prime by dx is the derivative of the natural logarithm of Vs prime. Okay. So, this is just equal to 3 by 2 natural logarithm of Vs prime, okay, the antiderivative, okay, which is equal to log of Vs prime whole power 3 by 2. Okay. Okay. So, that is the solution. Okay. This is equal to, okay. So, therefore, here I have exponential of the natural logarithm of Vs prime whole power 3 by 2, okay, which is equal to just Vs prime whole power 3 by 2. Therefore, the solution for delta x cubed is equal to constant by Vs prime whole power 3 by 2 plus integral 0 to x dx prime, okay, of I should have 1 over the integrating factor here. So, I will have 1 over Vs prime whole power 3 by 2 integral 0 to x dx prime, okay, of 3 alpha by Vs prime into Vs prime whole power 3 by 2. Okay, so, this is the final expression for the boundary layer thickness, and if we assume that the boundary layer thickness is 0 at x is equal to 0, that means this constant has to be equal to 0. Okay, that means that this constant has to be equal to 0. If we assume that the boundary layer thickness is 0 at x is equal to 0. Okay. So, this is the general solution, okay, for the flow past a surface at which the boundary at which the you have a no slip condition, that is the velocity decreases to 0 at the surface, flows past rigid surfaces such as a particle or a flat plate and so on. Okay. And you recall that we had done two problems here. One was the flow past a flat plate. Okay. One was the flow past a flat plate, okay, in which the velocity was increasing linearly from the surface, and the other was the stagnation point flow towards the surface. Okay. A stagnation point flow towards the surface, where the velocity was Vx is equal to k times x and Vz is equal to minus k times z. Okay. So, that was the velocity profile. In the former case, that Vs prime was a constant, okay, the strain rate was a constant independent of x. In the latter case, the strain rate was the velocity Vs prime at the surface. Okay. I am sorry, this is kxz and this was minus k. Okay. In the second case, the strain rate was linear function of x. Okay. It was proportional to k times x. Okay. And in both cases, you can use this formula in order to find out what is delta cubed and therefore delta, okay, and then integrate that. I will not go into the details, it is a straightforward substitution. Okay. The same formula does not apply for the flow around a sphere, for example. Okay. The reason is because the equation for the velocity profile is different in that case. Okay. Okay. For a spherical coordinate, the velocity condition, divergence of velocity is equal to 0. If you recall, this is 1 by r square d by dr of r square Vr plus 1 by r sin theta. Okay, for an axisymmetric sphere, okay, for an axisymmetric temperature profile around a sphere. Okay. So, this is different from the incompressibility condition that I had over here. Okay. This is different from the incompressibility condition that I had over here. Okay. So, therefore, I need to recalculate this relation between the strain rate at the surface and the two Vr and V theta in this case. Okay. So, this exercise I will leave it to you as an to do it as an exercise. You can still get the solutions in this case as well for an axisymmetric velocity profile. Substitute that into the conservation equation and get the temperature profile. Okay. So, what I have solved here is for a two dimensional case. Okay. You can do a similar calculation for the axisymmetric case as well, which I will not go through, but you will get the same a similar solution, which will turn out to be identical to what we had for the flow around a sphere if you substitute the velocities for the sphere. Okay, if you substitute the velocity approximation close to the surface for the flow around a sphere. Okay, so, this completes our discussion of the high Peclet number transport in the flow near a rigid surface, where the velocity has to decrease to 0 at the surface. Okay. The condition that the velocity has to decrease to 0 at a rigid surface, okay, implies that if I have a local coordinate system with coordinate x along the surface and z perpendicular to the surface, that means that Vx has to scale has to be proportional to Vs prime times z, and from mass conservation Vz is equal to minus V z square by 2. Okay. So, for z becoming small, the x component of the velocity is proportional to the boundary layer thickness delta. Okay. The streamwise component is proportional to the boundary layer thickness delta. The cross stream component is proportional to delta square. Okay. The cross stream component is proportional to delta square. So, if I substitute z is equal to delta times eta. Okay. If I substitute z is equal to delta times eta, right. My conservation equation is Vx, okay, times partial t by partial x plus Vz times partial t by partial z is equal to alpha times partial square t star by partial z square. Okay. You can see that this term is proportional to alpha by delta x square. Okay. This term is proportional to alpha by delta x square. Okay. Vx is proportional to delta. Okay. So, this is proportional to delta x. Okay. Partial t by partial x is scaled by the streamwise coordinate. Okay. X is scaled by the streamwise coordinate. So, this is just equal to Vs prime times delta x, okay, because x is scaled by the streamwise coordinate. Vz is minus dvs prime by dx times delta x square by 2, okay, and the derivative here is proportional to 1 over delta x. Okay. So, you can see that both the streamwise and the cross stream convection terms are of the same magnitude, because this delta cancels out and both of them are proportional to delta. Okay. Whereas, the diffusion term goes as 1 over delta square. Okay. So, in the limit of high Peclet number, this would imply that the delta x p e power minus 1/3. Okay. It would imply that the Peclet number goes as p e power minus 1/3. Okay. So, that is why you get this expression, okay, for the boundary layer thickness, and the heat flux q z is equal to minus k into T naught minus T infinity by delta goes as p e power plus 1/3. Because delta goes as p e power minus 1/3, that means that the flux goes as p e power plus 1/3. And that is the reason in all the correlations involving the flow past a rigid surface, the Peclet number always increases proportional to the Nusselt number always increases proportional to p e power plus 1/3. Okay. So, this completes our discussion of flow past rigid surfaces. Next class we will look at flow past a mobile surface, where the velocity is not 0 at the surface. Okay. If you recall, we had already seen this, the falling film. Okay. Okay. With a non-zero surface velocity Vs. Okay. We had solved this, if you recall, when we did the similarity solution for unsteady flows by making an analogy between the time for contact for an unsteady flow and the distance travelled for a steady but developing flow. Okay. So, if you recall, we had done this heat transfer in a falling film. Okay. And there we had got the expression for the temperature, or the, in that case I think it was a concentration, C star is equal to 1 minus root of 2 by pi times error function. No, it was just 1 minus error function of z by 2 root alpha t. Okay. That was the concentration, the scaled concentration profile that we had obtained. Okay. And we had made the analogy between the streamwise location from the start of the contacting section x. Okay. We had made the analogy between the streamwise location from the start of the contacting section x and t. Okay. So, t is equal to x by the surface velocity. Okay. That is the time elapsed as the parcel of fluid at the surface is moving, right, is equal to x divided by the surface velocity. This was assuming that the velocity is approximately a constant close to the surface. Okay. Okay. This was assuming that the velocity is approximately a constant is equal to Vs close to the surface, because the slope has to go to 0 in order to satisfy the no stress condition at the surface. Okay. And this we had seen this x Vs is equal to 3 by 2 times the average velocity. So, this was 2 V average by 3, I am sorry, 2x by 3 V. And on this basis, we had got the correlation for the Nusselt number or the Sherwood number in this case. Okay. This problem can also be solved systematically using the boundary layer procedure that I have just outlined for you, except that the velocity, okay, the velocity V x is equal to just V s, okay, the surface velocity, because the velocity is non-zero at this surface, in contrast to the flow past a rigid surface where the velocity was 0, and therefore, we had expressed the strain rate as the the velocity close to the surface as the product of the strain rate and the distance from the surface. In this case, the velocity is just a constant. Okay. That has to be substituted into the conservation equation V x partial t by partial x is equal to alpha times partial square t by in this case the concentration with the diffusion coefficient here. Okay. So, this has to be substituted in here and then use a similarity transform eta is equal to z by delta x of x. Substitute that in, use chain rule for differentiation and then get an expression which tells you what is the condition under which the similarity solution is possible. That will give us an expression for the boundary layer thickness. And at the end you should get the same result that we had obtained in when we solved this using a similarity transform. You should get the same result that we had obtained over here. So, I will leave that as an exercise. Next class I will examine the flow around a gas bubble, okay, do the same procedure for the flow around a gas bubble and get the Nusselt number correlation for that case. That I will continue in the next lecture. I will see you then.